Hi everyone, welcome back. In this video we're going to talk about symmetry that we see on the polar plane. We're also going to take a look at the other types of shapes that we see and what their equations look like for polar graphs. Okay, so we're starting off with symmetry. So just like on the Cartesian plane we have symmetry across the x-axis, the y-axis here, we can also talk about symmetry just using a few different words and using different tests. First is symmetry with respect to, I'll just shorten this to WRT, with respect to the polar axis. So instead of saying x and y axis, we'll be using different words because we don't have x and y for the polar plane. Instead, first we have the polar axis, which is just the axis here, left and right. And if something is symmetric across the polar axis, that means we can flip it horizontally, or sorry, flip it across the horizontal axis, so flip it vertically, and it'll match up exactly with the other side. We can tell if an equation is symmetric across the polar axis if we can replace the angle theta with negative theta and get the exact same equation. So if they match up exactly and it doesn't change the equation, then it is symmetric across the polar axis. Let's list out all the symmetries and then we'll go over a few examples. Next is symmetry with respect to the line theta equals pi over 2. And this line is just going to be in Cartesian coordinates, what we would consider the y-axis. So vertical line there. We can test for symmetry here by replacing theta with pi minus. Yep. Replacing theta with pi minus theta. So if you replace theta with pi minus theta and it matches up exactly, then your equation is symmetric across that line. And that means that it can be flipped horizontally across the vertical line. Theta equals pi over 2. Finally, the last type of symmetry is symmetry with respect to the pole. Symmetry with respect. So the pole is, another word for it is the origin in Cartesian coordinates. In other words, if we were talking about Cartesian coordinates, it'd be 0, 0. That point right in the middle. And if something's symmetric across the pole, that means we can take a point on our graph and flip it across the pole and it'll match up exactly. For example, if we took a point up here and flipped it across the pole, we would just flip to the exact opposite side, the same distance away from the pole. Flip it across the pole. For symmetry across the pole, we can tell if an equation is symmetric across the pole by taking a look at the r values. If we can replace r with negative r, so the same angle, if we flip the distance to go in the opposite direction and it matches up exactly, then it's symmetric across the pole. Okay, I want to take a look at a couple of examples. So first, let's just talk about symmetry across the pole. One quick example that we can look at is the equation of a circle. So we know a circle is going to be symmetric across a pole. And specifically a circle centered at the origin. Okay, so here a quick example would be a circle at the origin. And this one's kind of weird with the equation, but the equation we would have, for example, if we had r equals 3, that would be a circle with a radius of 3 at the origin. So we would have circle right about right here. If we replace r with negative r, in other words, r equals negative 3, no matter what angle we're at, instead of, for example, if we're at an angle of pi over 4, instead of being at 3, we'll be at negative 3. So we'll go in the exact opposite direction, but we'll also land exactly on our graph. where we would be at the opposite angle. So no matter what angle we're at, even though we have negative r, we'll flip across and end up exactly at the same spot on the graph. So circles, we can say, are symmetric with respect to the pole. Let's take a look at two more equations, and then we'll see what their graphs look like. So another equation I want to look at is the equation r equals 1 minus sine theta. Okay. I'll just label this A. So here we can do some tests for symmetry. First, we can check to see if replacing theta with negative theta gives us the exact same equation. If we were to do that, we would have r equals 1 minus sine of negative theta. And here, some of our even and odd properties are going to be helpful. If we think about our sine function and we plug in negative theta, what happens is we end up with a different sine value. So if you had sine of pi over 2, for example, pi over 2, and then you plugged in sine of negative pi over 2, you'll have, instead of 1, you'll have negative 1. So what that means is that it's not the same. 1 minus sine negative theta, not the same as 1 minus sine theta. So it's not symmetric across the polar axis. Next, we could check replacing theta with pi minus theta. Here, we end up with r equals 1 minus sine of pi over theta. And here we actually have a special situation where if we take sine and we take the sine value of, so that should be theta, pi minus theta, we end up with the exact same sine value. So if we were to take pi over 3, for example, and we took sine of that, and we also took sine of pi over 3, and we also took sine of pi minus pi over 3, so starting at 180 and then going back, we would end up with the exact same value because it's the same y value at that point. So this is the same, which means we do have symmetry symmetric across the y-axis, which is really just the line theta equals pi over 2. Okay. One more quick example. If we had r equals 1 minus cosine theta, and we were to check this replacing theta with negative theta, again, we would have r equals 1 minus cosine of negative theta. And here, thinking about our even and odd properties, cosine of negative theta does give us the exact same value as cosine of theta. And that's because if we take cosine and we take cosine of pi over 4, we would get root 2 over 2. If we took cosine of negative pi over 4, we would also get root 2 over 2 because we're looking at that x value on the x value on the plane. So here, this is the same as 1 minus cosine theta, which means in this case we have symmetry across the polar axis. Okay, so what I want to do next is take a look at the graphs of these and see what the symmetry looks like. All right, so taking a look at a couple of these graphs. So the first equation we had was r equals 1 minus sine theta. And as you can see, we end up with this graph that's kind of like a circle, but it has this little indentation in the middle. So kind of like a heart shape in a way. Here we can see that we have symmetry across the y-axis, the line theta equals pi over 2. And what that means is that if we were to graph half of this, if we were to graph, for example, the left half of this, if we were graphing this by hand, maybe, we only had to graph half of the points. And then what we can do from there is just copy all these over, flip them to the other side, and we'll end up with the entire graph of this function. So symmetry can be really helpful when we're graphing, especially if we're graphing by hand. We only have to graph half of the points, and then we can just copy them over to the other side. The same exact exact scenario can be seen for 1 minus cosine theta. Here we have symmetry across the polar axis, the x-axis, which means if we were to only graph half of the points, for example, above the polar axis, we would just have to take all of these, flip them across, copy them, and we would end up with the entire graph. These two graphs are examples of what we call cardioids, which is our first shape that we're learning. That's kind of a new shape of polar graphs. So let's take a look at the equations of these. Okay, so here we have our first shape, which is what we call a cardioid, cardioids. And I believe these mean or have a similar meaning to heart shapes, so kind of like hearts. The bottom isn't pointed though, it's rounded, kind of like a circle, and they have that indentation. As you can see, we have two different types of equations that end up with cardioids. R equals a times 1 plus cosine theta, also a times 1 minus cosine theta, so I just put them together, 1 plus or minus cosine theta. Also a times 1 plus or minus sine theta. Another way we can see these two is if we just have a plus or minus a times sine theta, so just distributing them. In other words, we have some number and that exact same number as a coefficient in front of sine squared or cosine squared. If we have cosine squared, we're going to have a shape similar to this, where it's symmetric across the polar axis. It could be facing the other way though, depending on the sign. If it's sine, then we'll have symmetry across the theta equals pi over 2 axis. And again, it could be upside down depending on the sign. Okay, so this is the first shape that we're learning that's brand new. We've learned about lines and circles, but this is our first new shape for different polar graphs and polar equations.